In this lecture, we address a fundamental concept called the Nernst equation or the Nernst equilibrium that is foundational to bioelectrical signaling in neurons as well as other cells. And the Nernst equation per se is an equation that attempts to quantify what's called the equilibrium potential for a particular ion. And we use the symbol S here just as a placeholder, as a variable, indicating that we can fit any ion into this equation to calculate what's called its Nernst potential. And the Nernst equation or Nernst potential is named after Walther Nernst, who won the Nobel Prize in 1920 for his work in thermochemistry. And what we're looking at here is what's called the Nernst potential, E for potential. The N should be a subscript, but it is a little bit smaller here for Nernst potential. And this is calculated for a particular ion where R represents a constant, Z is the charge on the atom by its valence, F is another constant called Faraday's constant, and En is the voltage difference or the Nernst potential across a membrane to hold that ion in equilibrium, the equilibrium determined by the balance of the concentrations on two sides of a cell membrane. And as an example, if we take a look at the Nernst equation for the sodium ion, we use the same equation, but with the difference is that the numerator is the exterior or outside cell concentration, and the denominator is the interior concentration. And note, this is the sodium ion, so there should be a plus sign, a plus superscript on both of them. Once again, the O indicates the outside of the cell, I is the inside of the cell, and this is an abbreviated form of the equation where the ratio of the constant to the temperature to the Faraday's constant is summarized at 37 degrees C to be a value of 26.73 millivolts. So this simplifies this equation in determining what the equilibrium potential is for sodium. So for example, if we take the exterior concentration of 145, the interior concentration at 12 millimole, and put that into the equation, the ratio is first determined, and then we calculate the natural logarithm of the exterior to interior ratio for the sodium ion of a cell in a resting state. We can calculate the Nernst potential. So in calculating that value, we come up with positive 67 millivolts. If we repeat that for potassium, we would end up with a value of approximately negative 98 millivolts. And so what these values mean, if we just look at sodium here, to hold sodium in what's called an equilibrium concentration, and as a reminder, equilibrium does not mean equal because we have 145 millimole outside and 12 millimole inside. To hold it at this concentration difference, we need a voltage difference of plus 67 millivolts on the inside of the cell with respect to the outside. And the key concept here in understanding this is that opposite charges will attract, so positive and negative will attract, and like charges will repel. And this is what we refer to in terms of polarity of a cell. That's the positive or negative. So the first question here is, what is the effect of a positive voltage inside the cell on sodium? And so we did calculate that as the Nernst potential for positive 67. And if we have a positive 67 environment inside the cell with respect to the outside, like charges will repel, so the positive 67 will repel the positive sodium to stay outside of the cell, and that's what's needed to maintain the concentration balance. The next question is, what is the effect of a negative voltage inside the cell on potassium? And so now we go to the first item of our key concept, in that opposite charges attract. If we have a negative voltage environment inside the cell, the negative and positive will attract, and that environment will keep potassium inside the cell. So potassium stays in the cell. Now, in reality, what exists for a muscle cell or a neuron for that matter? Because the Nernst potential focuses on each ion in complete isolation, in reality, we have cells such as a muscle cell where the interior of the muscle cell in a resting state is actually negative 65 millivolts on the inside with respect to the outside. And that's referred to as the reversal potential. Where we take into consideration simultaneously the actions on the environment with respect to the actual driving force for various ions. And so in this equation, we're simultaneously considering the concentration of potassium, sodium, and chloride, whether it's outside the cell or inside the cell. And likewise, we have in the denominator the interior concentration of potassium, the interior concentration of sodium, and the exterior concentration of chloride. Now, these are all ions, and they should have positive or negative symbols associated with it. The P refers to the permeability or the relative ease at which an ion can move from one side or the other. So the reversal potential, or EREV, is also referred to as the zero current potential. So the potential to ensure that there is no movement or zero current of ions into or outside or moving out of the cell. And this value is essentially the weighted average or the weighted mean of all ion effects, where P once again refers to the permeability of the cell to that ion, which is multiplied by the concentration outside the cell, in this case of potassium, and then that's added to the product of the permeability of sodium for that particular cell times its exterior concentration, so on and so forth. And when we look at permeabilities, the ratio of the permeability of potassium to sodium for a sodium channel, we see that it's very, very low. That tells us that sodium channels are uniquely specific to sodium ions. If we take a look at the permeability of protons to sodium ions, it's actually quite high through a sodium channel. So this very high value tells us that protons are much more permeable than sodium ions through sodium channels. As another example, if we take a look at the permeability of sodium through potassium channels, we see that that ratio is actually quite small through a potassium channel, suggesting here that potassium channels are uniquely designed for just potassium ions. What we're going to look at here on this slide, and we will revisit this slide in a subsequent video, this refers to the actions of neurotransmitters on the state of sodium outside the cell and inside the cell. So that will occur through sodium channels. So on the upper left-hand side, what we see is a drawing of what's called the nicotinic acetylcholine receptor. And this exists on a skeletal muscle cell on what is called the postsynaptic membrane. So we have a synapse between the terminal part of a motor neuron where it essentially connects to a muscle cell. For the neuron to communicate with the muscle cell, the terminal part of a motor neuron, which is its axon, will release neurotransmitter. That particular neurotransmitter is acetylcholine. So in this drawing, what we see here is when acetylcholine, not just one, but two acetylcholine molecules bind to the postsynaptic sodium channel, that is a ligand-gated sodium channel. And that will cause the protein to change shape slightly. And when that happens, we see that these sodium ions will move through the channel and enter the interior of the membrane inside the cytoplasm. When that happens, that will take a resting state sodium channel, which is a voltage-gated sodium channel. And so if we extend the membrane of a muscle cell, we see that we have a slightly different type of sodium channel. This slightly different type of sodium channel is not in proximity to the axon, but is located downstream a little, if you will, in the membrane from the ligand-gated sodium channel, also referred to as the acetylcholine receptor. So once the ligand opens up this particular channel, sodium rushes in, and then sodium will find its way to the voltage-gated sodium channel and will open it. So in the resting state, we have something called an activation gate, which is a schematic that is closed, but the negative inside charge changes to positive. So as we add these positively charged sodium ions to the interior of the cell takes on a positive environment. Remember the first principle that a small, very small movement of ions to one side or the other will have dramatic effects on the electrical environment. And that will open up a channel which is voltage gated and cause what's called depolarization. So in the resting state, the muscle cell here is polarized on the inside where it has this negative charge. When it depolarizes, it becomes positive on the inside with respect to the outside, which is more negative. And this process is very, very fast, on the order of milliseconds, 1 or 2 milliseconds. And so the massive rush of sodium to the interior of the cell will cause that change. And that opens up the activation gate. And the activation gate comes by way of weak binding of sodium on the inside of the cell, and it's transient. Now, that will trigger relatively quickly a slow closing of that gate. So we have a very fast opening that will trigger a slow closing of what's called the inactivation gate. So the inactivation gate will, you can see here, hold the cell in a depolarized state, but in the depolarized state, the sodium channel remains closed. And that's an advantage here because that will allow the cell to repolarize, bringing it back to its resting state. The mechanisms of repolarization involve the movement of potassium, which is not illustrated here on this slide. And it's something that we'll address in a subsequent video. So this ends this video on the Nernst potential and the introduction to the sodium channel.